Okay, so for graphs, velocity versus acceleration, all you need is this paper, but 5 colors. So just cut the border off, glue it in, but glue it in with glue it in with 2 lines of space above it. Okay, just put glue on the border because we're going to be writing on this a lot, so to not have sog. Remember we talked about displacement versus time graphs? That's kind of like the same thing as a position versus time graph. Or as a distance versus time graph. We kind of read them all the same way. Okay? We've discussed this before, that the slope in a displacement versus time graph, what does the slope tell us? The slope tells us the velocity of the object. Now, the reason why the slope tells us the velocity is because of the formula for velocity. Velocity is displacement divided by time. Okay? Displacement divided by time. Displacement and time are 2 variables. When we combine the ideas of displacement and time, putting displacement on the y-axis and time on the x-axis, we essentially divide them. The result is a line. That line is the slope. That slope is therefore the velocity. Okay? That's why the slope in a displacement versus time graph is the velocity. Important note right here, where the displacement, position, or distance is equal to 0, what do we call that? Reference point. Okay? In a displacement versus time graph, the displacement of 0 is the reference point. That is important because that tells us position in space. When you see a straight line, when we graph a straight line, all right, what is the algebra, mathematical, scientific, official word for a straight line when we're dealing with a graph? Linear. Okay, so when we have a linear graph, linear means that something is constant. Constant just means it's not changing. So something is constant if we have a linear graph. And we are going to draw a graph that represents a constant, fast velocity. Is it going to be linear? Is something about it constant? Yes. Yes, the velocity is constant. So if the velocity is constant, it's going to be linear in a displacement versus time graph. Now, the fact that it's fast, what does that tell us? Steep slope. All right? So nice steep slope. Let's do a constant, slow velocity. Is it linear? On a displacement versus time graph? Yes. Okay, so the slope is the velocity in a displacement versus time graph. If the line is linear, if the graph is linear, that means the slope is constant. The velocity is constant. Okay? Yes? So in a displacement versus time graph, if the graph is linear, the velocity is constant. So we're dealing with a slow, constant velocity. We have another linear graph. Okay? But it's going to be slow. So just a little bit of slope. Next, let's talk about something that's at rest. So I'm going to use green. What does at rest look like in a displacement versus time graph? Is it linear? It is. But what's special about it? Linear means straight. It's horizontal. Okay? So I'm just going to, right here, we'll say it's 6 meters from the reference point, and that's its position, and that position does not change. Now, I said linear is constant, right?
Yes.
So what's so constant about the at rest?
Doesn't move.
You can say it's a constant velocity of 0, or you can say it has a constant position. Constant acceleration. Now, acceleration is not what our slope is telling us here. Our slope is telling us the velocity. What's the definition of acceleration?
You change in the speed or velocity.
The velocity is changing. So in our graph, on this one, the velocity is changing for an acceleration. Okay? This one will not be linear, but you're going to see that constant acceleration over here will be linear. All right, so constant acceleration. Starting off with acceleration, you start off slow and then you go faster and faster. So I'm going to start at the 2, displacement of 2. Start off kind of horizontal for at rest, going faster and faster and faster and faster and faster and faster and steeper and steeper and steeper slope. That would be an acceleration. Sorry. And then my last color, red. Now I'm going to do a constant deceleration. You probably noticed by now that if this isn't done in color, it means absolutely nothing, because you have to match the color of the words with the color in the graph. So it has to be done with colors. Otherwise, it means absolutely nothing. It's a worthless journal entry if it doesn't have colors. Okay, so constant deceleration. All right, with constant deceleration, it starts off steep because it's going fast and then slows down. Okay, so starting off fast. Okay, I'm going to start like here at the 1. Nice and steep, and then it curves out till it kind of levels off at rest. Now we're going to take all those exact same movements. All right, the constant velocity, the slow velocity, the at rest, the constant deceleration, the constant. We're going to do all 5 of those motions, and we're going to regraph it in a velocity versus time graph. Okay, so in a velocity versus time graph, does anyone remember what slope is, or what the slope tells you in a velocity versus time graph? Here's your little hint. The change in velocity and the change in time. As time changes, velocity changes. Change in velocity, change in time. What changes? What's happening if velocity is changing over time? We have acceleration. All right? I'm going to show you what I'm talking about here. What I'm about to write, you don't have to write your notes. I'm just writing it for clarification. This is totally optional. I'm going to do it on the oops page. So acceleration is the final velocity minus the initial velocity over the change in time. Okay? Well, acceleration can also be written as the change in velocity is over the change in time. That literally means the final minus the initial. Final velocity minus initial velocity. That's what the delta V means. Okay? So acceleration only happens, an object's only accelerating if the velocity is changing. Okay? So a little note here. If you have a constant velocity, that means the speed and the direction do not change. Acceleration by definition means the velocity is changing. So the speed and or the direction are changing. Usually just the speed's changing. Okay, like I said, you don't have to write those in. I just wanted to clarify that. So, back to our graph. As the if the velocity is changing as time passes, then the object must be accelerating. Okay, this is a poorly drawn graph. I'm just gonna, sorry, didn't photocopy very beautifully. Gonna fix that before I move on. So, the slope in a velocity versus time graph tells us what? The acceleration. All right, so find your color for constant fast velocity. In a velocity versus time graph, a constant fast velocity. What is that going to look like? It's constant, right? So we can anticipate it's going to be linear. The velocity is fast and it's not changing. So we'll call this is obviously at rest, we'll call this slow, medium, we'll go with fast up here. Okay? So it's fast. A second later, it's still the same fast. And a second after that, it's still going fast. And you end up with a fast constant velocity. You end up with a horizontal line in a velocity versus time graph. The velocity is not changing, it's not decreasing. The velocity is not increasing, it's staying the same. A fast constant velocity. Now wait a second here. We said that the slope, bless you. In a velocity versus time graph, the slope is equal to the acceleration. So my question is this. With a fast constant velocity, what is the acceleration of the object if it has a fast constant velocity? All right, so constant velocity means that the velocity is not changing. Acceleration means the velocity is changing. So if the velocity is not changing, what's the acceleration? 0. Check out that slope. So think back to your algebra class. What's the slope of that line? It's 0. It's not positive, it's not negative, it's in between. What's between positive numbers and negative numbers? 0. The slope is 0. It has no slope. It's a constant velocity. Cool? All right. So let's try constant slow velocity. Pick your color for constant slow velocity. I've got purple. So constant slow velocity. So we said this was a fast velocity. Here's a medium velocity. Let's go with the slow velocity down here. Okay? It's slow. A second later, it's still the same slow. And a second after that, it's still the same slow. And its velocity is not increasing. It's not going faster. It's not going slower. It's just staying right there at that same velocity as time passes. So a constant slow velocity, just by looking at the graph, what's the acceleration of that object? 0. Because in a velocity versus time graph, the slope is the acceleration. That slope is 0. The acceleration of the object must be 0. Okay. At rest. Okay, so if you're at rest, I'm going to ask this question first. What's your velocity equal to if you're at rest? 0. Okay, so in my velocity versus time graph, if my velocity is 0, where am I? Velocity equal to 0, right here. So there we go, velocity equal to 0. And then a second later, it's still 0 because you're still at rest. And after that, it's still at rest. And then still at rest and still not moving, and the velocity is still 0, and it's still 0, and it's still 0. So, if you're at rest, what's your acceleration?
0.
Your acceleration is 0. Okay? You could, like I said before, you could think of this as a constant position. This is the one graph in both of these that's horizontal. At rest, in a displacement versus time graph and in a velocity versus time graph, they're both horizontal. The difference being is that this one is at the 0. Okay? So notice right here on a velocity versus time graph, this is not called the reference point. We do not know position in a velocity versus time graph. So it is not the reference point like it is in a displacement versus time graph. This is simply at rest. Okay? Does that make sense? That axis is considered at rest, where this axis was considered the reference point. All right. Constant acceleration. Find your color for constant acceleration. All right. When we're accelerating, the velocity, all right, the velocity is changing. How is the velocity changing if you're accelerating? It's increasing. Increasing. Okay, so here we go. You're going to be going faster and faster and faster. This one over here, we started pretty much at rest, so let's start at rest here, velocity of 0. And then a second later, you're going faster, and then faster, and then faster, and then faster, and faster, and faster, and faster. But every second, we increase the velocity by the same amount. That's what makes a constant. In this case, we're increasing by 0.5 meters per second every second. So we get a linear, constant acceleration. If it was kind of a jagged or swervy line moving up, it would still be accelerating, just not constantly. Cool? So So if you think back to the lab on the acceleration ramp, all right, the little balls rolling down the ramp. When we graphed this line, I made it a line of best fit on the graph, okay? Because there's a bunch of little dots that were all kind of lined up, but not perfectly. Those that slightly off a little bit is because your ramps were not perfect and the balls are not perfect, and there could be a little bit of dust on the ramp, and that could have slowed it down, and so there's all sorts of little factors in there. But ideally, it would have been perfectly linear because gravity is what's pulling on it, and gravity is a constant pull. That's kind of an introduction into the next topic we will do after we finish graphing. Okay? All right. Last graph, constant deceleration. So if you have deceleration, the velocity is changing. What is happening if the velocity is changing and we're decelerating?
It's decreasing.
It's decreasing. All right. Sorry. Here we go. So what's that going to look like on our graph? Well, we're going to start off going fast. And we're going to decrease. This time we're going to do 1 meter every second. So in 1 second, we'll decrease by 1 meter per second. During the next second, 1 meter per second. During the next second, another meter per second. And the next second, another meter per second. Okay? So a deceleration. The velocity is decreasing every second. Okay? Does that help?
Yes, ma'am.
A little bit of comparison there. See it side by side. Hopefully that clarifies a little bit on the graphs. Okay.